This question was asked from the GATE Physics paper 2021. This is a multiple select question of 1 marks, and this question was asked from the topic electromagnetic theory. The question is, a material is placed in a magnetic field intensity capital H. As a result, bound current density JB is induced and magnetization of the material is capital M. The magnetic flux density is capital B. Choose the correct options valid at the surface of the material. Option A is divergence of M equals to 0. Option B, divergence of B equals to 0. Option C, divergence of H equals to 0. And the last option, option D, divergence of JB equals to 0. Now, as this is a MSQ, so it is possible to have multiple options correct. We'll check each and every options one by one. Let us see the solution part now. Before going to the solution part, we will first recap some basics related to the magnetic material in a magnetic field. We know magnetization of a magnetic material when it is kept under an external magnetic field B, it provides us with a macroscopic description of the atomic currents in the matter. Mathematically, magnetization of a material is defined as summation over all the magnetic dipole moment of the matter divided by a volume element when volume tends to 0. Here, magnetization of the system is a macroscopic quantity, but your magnetic dipole moment is a microscopic quantity. If we want to visualize what is the magnetization of a system physically, we need to consider tiny current loops formed in the matter due to the cyclotron motion of the electrons when the material is kept under a magnetic field. Now, this tiny current loop will have some magnetic dipole moment. These magnetic dipole moments will basically contribute to the magnetization of the system. Now, for uniform magnetization, the volume bound current density Jb is 0, but the surface bound current density Kb is non-zero. This is because for uniform magnetization, all the tiny current loops formed inside the bulk of the system will cancel each other. Hence, you will have a 0 volume bound current density Jb. But at the surface, the cancellation will not happen. So, effectively, you will have a non-zero surface bound current density Kb. In the case of non-uniform magnetization, both the current densities Jb and Kb are non-zero. Now, we'll try to relate these current densities Jb and Kb to the magnetization of the magnetized material. For this, we'll consider a magnetized material kept under an external magnetic field B, and the system will have volume V. Inside this system, we'll consider elementary volume dV, whose coordinates is x dash, y dash, z dash from the origin. And we'll consider another external point P, which has the coordinate x, y, z. So, from the volume element, the external point P will have position vector capital R, which is basically your R vector minus R dash vector. Now we know vector potential due to single current loop having magnetic dipole moment small m is given by mu naught by 4 pi m cross r by r cube. Now for a magnetized material having magnetization capital M, the vector potential A vector is given by mu naught by 4 pi integration over m vector dv cross product with capital R vector by capital R cube. Now, after some simplification with the help of vector algebra, we can show this A vector is basically summation of two terms. Now here the first term is due to the contribution from the volume of the system, that is the bulk of the system, but the second term is due to the contribution from the surface of the system. And from the first part, this curl cross M is basically your volume bound current density. And in the second term, the m cross n cap, this is your surface bound current density. Hence, the volume bound current density is defined as Jb equals to curl cross m vector, and surface bound current density is Kb equals to m cross n cap. Now we'll see the solution of the given question. We have already seen when magnetic material is placed in a magnetic field, it will get magnetized, and it will give rise to two types of current densities, that is volume bound current densities and surface bound current densities. The volume bound current density is given by Jb vector equals to curl cross m, and your surface bound current density is Kb equals to m cross n cap. Now we know the magnetic flux density or magnetic field inside the material is given by mu naught times your H vector plus the magnetization vector m. Now from the Maxwell's equations, we know divergence of B vector is 0. For a magnetized material, this B vector is mu naught times H vector plus m vector. If we put that relation in the equation, then you will get mu naught times divergence of H plus divergence of m equals to 0. It will basically give divergence of H equals to minus of divergence of m. Now our system has a volume bound current density Jb. This means our system has non-uniform magnetization. So the divergence of m vector for this system is non-zero, and it will give rise to divergence of H is non-zero. Now divergence of Jb is divergence of curl cross m, because Jb is defined as curl cross m. And this term is also 0, so your divergence of Jb is 0. So if you see the four options, among the four options, this B option and the D option is correct. According to our solution, the option B and option D, those are divergence of B equals to 0 and divergence of JB equals to 0 are the correct options for this question.